Welcome to part 5 of this video playlist about the preparation of alkynes. This video is about the acylation, carboxylation and cyanation of terminal alkynes. This yields electron-deficient alkynes that are excellent Michael acceptors because of the intrinsic electrophilicity of alkynes and because of their high sterical accessibility. These products react readily with nucleophiles, even weak ones, and it can be difficult to prevent such additions. Fortunately, some strategies have been developed that enable the preparation and isolation of electron-deficient alkynes in high yield. Let's start with acylations. These can proceed both under alkaline or acidic conditions, as sketched here. Examples of base-induced acylations would be the treatment of lithium acetylides with esters or Weinreb amides. Under acidic conditions, non-deprotonated or silylated terminal alkynes could, for instance, be acylated with acyl chlorides or anhydrides. During workup, care must be taken to prevent the addition of nucleophiles to the target enone. Let's check some specific examples. Here, monosilylated acetylene reacted cleanly with a substituted benzoyl chloride under standard Sonogashira conditions with one equivalent of triethylamine as base. The reaction was complete after only 1 hour at room temperature. This example is quite remarkable. Acyl chlorides with alpha hydrogen react explosively with triethylamine to ketenes. The latter are also electrophilic acylating reagents, but may also dimerize or undergo 2+2 cycloadditions with alkenes and alkynes. Nevertheless, the expected enone was formed here in acceptable yield. This is another remarkable example where the acylation was conducted in a biphasic mixture with copper and palladium catalysts, aqueous carbonate as base, and a phase transfer catalyst. In fact, hydrophobic acyl chlorides can be quite resistant to hydrolysis, in particular when dissolved in dichloromethane or toluene. In this example, a copper acetylide was acylated with benzoic acid activated as mixed anhydride, again under standard Sonogashira conditions. Despite the high reaction temperature, no decarbonylation occurred. In parts 3 and 4, there are examples of similar reactions where the activated carboxylic acid undergoes decarbonylation and the alkyne is arylated or vinylated, but not acylated. These reactions, however, required temperatures of about 150 degrees Celsius. Amides can be converted into more reactive acylating reagents by alkylation or sulfonylation at oxygen. Here, an amide was activated with triflic anhydride and then treated with an isolated copper acetylide. An acceptable yield of enone resulted. One convenient strategy for preparing ketones is the addition of carbon nucleophiles to nitriles. In this example, catalytic amounts of a lanthanum silyl amide brought about the acylation of 1-hexyne with benzonitrile at room temperature. Similarly reactive as nitriles are Weinreb amides. Here, treatment of an aspartic acid-derived Weinreb amide with an excess of lithiated alkyne gave a moderate yield of the target ketone. Aldehydes are often prepared by adding DMF to polar organometallics. This also works with lithiated terminal alkynes, as shown here. However, the enone could only be isolated if the reaction mixture was poured slowly into an acidic buffer. Otherwise, if during hydrolysis the mixture became alkaline, dimethylamine added irreversibly to the CC triple bond of the product. In this example, silylated acetylene was first hydroxyalkylated by an aldehyde and then oxidized to the target ketone. The required aldehyde was also generated by oxidation with the same ruthenium catalyst. No stoichiometric oxidant was required and hydrogen must have been a byproduct. Another way to acylate or carboxylate terminal alkynes is by transition metal catalyzed carbonylation. Insertion of carbon monoxide into, for example, palladium-carbon bonds yields acyl complexes, which can react with various nucleophiles to yield carboxylic acid derivatives. If a terminal alkyne is carboxylated this way, the palladium-2 catalyst is reduced to palladium-0 and must be reoxidized to the active catalyst. The intermediate palladium-acyl complexes can also react with other nucleophilic organometallics to ketones. In this example, phenylacetylene was carbonylated with a palladium catalyst and then converted into a phenyl ester. Palladium-2 was regenerated by oxidation with benzoquinone. Here, carbon monoxide was generated by dehydration of formic acid with a carbodiamide. No oxidant was required in this case because the active catalyst was palladium-0. Oxidative insertion into the carbon-iodine bond gave a vinyl palladium iodide, which reacted with the alkyne to a vinyl alkenyl palladium complex and iodide. Reductive elimination then regenerated palladium-0. Also, arene diazonium salts can serve as precursors to organopalladium intermediates. Despite the complexity of this 9-component reaction, the target enone was obtained in acceptable yield. The formyl group remained unchanged. Sonogashira couplings with unprotected propiolic acid can surprise us with unexpected results. Because terminal alkynes are acidic, propiolic acids readily decarboxylate, as in this example. The resulting terminal alkyne was carbonylated and then arylated to an enone in fair yield. Carbon dioxide is a relatively weak electrophile. Some metallated terminal alkynes do, however, react with carbon dioxide, and upon hydrolysis and careful acidification, substituted propiolic acids may result. The intermediate carboxylate can also be alkylated with alkyl halides or sulfonates and yield esters directly. Nickel or palladium propiolates do occasionally cyclize, though. The intermediate vinyl complexes can, for instance, react with one further equivalent of carbon dioxide to maleic acid or its anhydride, or be hydrolyzed to acrylates. Instead of carbon dioxide, other electrophiles that react with metallated terminal alkynes include phosgene, chloroformates, carbonates, isocyanates, isonitriles, and carbodiamides. In this interesting example, substituted phenylacetylenes were carboxylated without stoichiometric metallation, just by stirring at room temperature with an excess of carbonate and acetate under an atmosphere of carbon dioxide. The brominated phenylacetylene yielded the expected acid, but nitrophenylacetylene was probably too acidic and the acetylide therefore not nucleophilic enough to add to carbon dioxide. This here is an example of the alkylation of an intermediate cesium propiolate. Carboxylates are not very nucleophilic, and their alkylation requires highly reactive alkylating reagents, such as alkyl iodides, triflates, or diazoalkanes. Allylic or benzylic chlorides can also be reactive enough to alkylate carboxylates. Here, a copper acetylide was treated directly with an allyl chloride and carbon dioxide. The expected allyl propiolate was the main product, and only traces of an allyl alkyne resulted. If instead of a copper-carbene complex, copper bromide was used as catalyst, the carboxylation was much slower, and a mixture of products resulted. Copper acetylates show some radical character and can form C-C bonds with other carbon-centered radicals. In this example, an aminocarbonyl radical was generated by oxidation of DMF in the presence of a terminal alkyne and catalytic copper dichloride. Mainly the target amide was formed, without cleavage of the carbon-bromine bond. When metallated terminal alkynes add to isonitriles, the first intermediate is a carbene. These can be stabilized by coordination to various transition metals, which will therefore promote and catalyze this first step. Protonation then yields an imine, which may be oxidized to an amide or react with one further equivalent of metallated alkyne. In this example, 10% of a samarium amide catalyzed the addition of one hexyne to a sterically shielded isonitrile. An imine was formed in high yield. In the presence of one equivalent of silver nitrate as oxidant, however, instead of imines, amides can result, as shown here. No strong base was required, just 5% of a cobalt-phosphine complex. With stoichiometric copper acetate as oxidant, ketone-derived imines can be obtained from alkynes and isonitriles. Only traces of diines were formed by Glaser coupling under these conditions. Let's now have a look at the copper-mediated cyanation of terminal alkynes. Mechanistically, this reaction is related to the oxidative Glaser coupling of alkynes to diines and to the formation of cyanogen from cyanide and copper-2 shown here. The structure of copper acetylides or cyanides is such that the two copper-bound carbon atoms are quite close to each other. Then the copper-carbon bonds in these compounds show some diradical character, and copper-2 is a sufficiently strong oxidant to generate carbon-centered radicals by single electron abstraction. Dimerization of these carbon-centered radicals then yields the final product. Copper-1 cyanide is an insoluble polymer, but with an excess of cyanide, a soluble dicyano-copper-1 anion is formed. The mechanism of copper-mediated cyanations of terminal alkynes lies probably between the formation of cyanogen and of diines. Oxidation of a mixed cyano-copper acetylide would yield carbon-centered radicals, which could dimerize to the observed cyanoalkynes. Potential byproducts include diines, halogenated alkynes, cyanogen, and the addition products of cyanide to cyanoalkynes. The latter will be formed if the excess of cyanide is too large, the former if too much copper-2 and too little cyanide was used. Thus, alkyne cyanations may require some optimization, and yields tend to be low. In this example, a terminal alkyne was treated with a large excess of copper-1 cyanide and chlorotrimethylsilane. Oxidation was probably brought about by the mixture of DMSO with the chlorosilane. Despite the excess of reagents, the yield of cyanoalkyne was only 48%. Also in this example, a huge excess of reagents was used. These were sodium cyanide, copper-2 perchlorate, imidazole, and DPA and THF. No substitution of chloride by cyanide occurred, because the solubility of sodium cyanide in organic solvents is low. Because of its small size and high electric field strength on its van der Waals surface, cyanide forms strong hydrogen bonds with water and tends to act not as a nucleophile but as a base. Also, iron trichloride can be used as oxidant for the cyanation of alkynes. In this example, a small amount of chlorinated phenylacetylene was formed as byproduct. Here, a terminal alkyne could be cyanated with an excess of cyanogen iodide and a catalytic amount of copper-1 triflate. The main problem of cyanogen halides is that these often act as electrophilic halogenating reagents. In this instance, however, the main product was the target cyanoalkyne, and less than 10% of iodinated olefins were formed as byproducts. Another suitable source of cyanide for copper-catalyzed cyanations is AIBN. Here, a substituted phenylacetylene was cyanated in acceptable yield with 2 equivalents of AIBN and 20% of copper nitrate in refluxing acetonitrile. Interestingly, the cyanation required oxygen. When conducted under an inert gas, mainly the product resulting from reductive addition of a cyanopropyl radical to the triple bond was obtained. So, how does this work? It is known that AIBN fragments upon heating into nitrogen and 2 cyanopropyl radicals, and is therefore often used as a radical starter. These 2 cyanopropyl radicals react with oxygen to an oxygen-centered radical, which, according to the various bond strengths involved, should fragment into acetylcyanide and a methyl radical. Formation of cyanoradicals and acetone is less likely because of the high energy of the cyanoradical. On the other hand, copper readily binds to carbon-centered radicals, and bonds with cyanide are particularly strong. Thus, the oxygen-centered radicals may react with copper acetylides directly to yield cyanated copper acetylides and finally, after reductive elimination, the observed cyanoalkynes. The reductive cyanopropylation of the alkynes may proceed as sketched here. The only potential source of hydrogen was AIBN, and hydrogen atom abstraction would yield the cyanopropylalkene along with metacrylonitrile, nitrogen, and a new 2-cyanopropyl radical. Let's check some potential side reactions. As mentioned, all the products shown above are strong Michael acceptors, which readily react with all kinds of nucleophiles. Simple Friedel-Crafts acylation of terminal alkynes, for instance, usually yields chloroenones, as in this example. Palladium or nickel-catalyzed carboxylation and carbonylation of terminal alkynes can yield acrylates instead of propiolates. Here, an acid and palladium-catalyzed carbonylation mainly yielded a mixture of two isomeric methyl acrylates. Electron-deficient alkynes will readily add cyanide, but so do even non-activated alkynes. Hydrocyanations are often catalyzed by nickel, but other transition metals can also bring about this reaction. Here a rhodium-phosphine complex was used. In this example, a terminal alkyne was converted into substituted acrylonitrile by treatment with zinc cyanide and a nickel catalyst. When trying to carboxylate terminal alkynes with carbon dioxide, oxidative dimerization may occur, as in the first reaction shown here. Still much stronger oxidants than carbon dioxide are phosgene and trifluoroacetic anhydride. Propiolic alcohols can also form cyclic carbonates when treated with carbon dioxide, like in the second example. Under forcing conditions, palladium-catalyzed carbonylations of terminal alkynes can yield succinates, as in this example. As I said at the beginning, acceptor-substituted alkynes are highly reactive and will only be obtained if the reactions are stopped in time and the workup is done carefully. Here are some further examples which you can also find in the description of this video. Under the Community tab of my channel, you'll find a PDF version of the slides. The next video of this playlist is about the preparation of alkynes by isomerization and alkyne metathesis. So long.